Okay, so we haven't talked yet about standing waves, but if we were in the classroom, I'd be doing a demonstration with you in which one person would be holding one end of a slinky on one side of the room and another person, probably me, would be holding the other end of the slinky. Now, I would be generating a periodic wave in that slinky. And if I were able to do this demo successfully, which usually I am, and by the way, I'm going to try and get into the classroom next week so I can get my hands on all the materials I need for all the demos that we have not yet gotten to do for this unit. So basically, I'd be generating a periodic wave with that slinky. However, this person over here represents a fixed end. So yes, I'm sending this periodic wave this way. However, once this wave reaches this fixed end, it's going to invert itself and reflect off of the fixed end. This is something I had mentioned back when I was talking about wave behavior at a boundary. So because this wave is encountering this fixed end, the force acting in the opposite direction is going to invert it. And what you will end up seeing is something that we would refer to as a standing wave. And it would look something like this. So you're going to essentially see two waves. Sorry. I'm not sure if that got blurry or not. Okay. You'll essentially see two waves. One will be the actual transmitted wave, which I have shown in black. So I'm just going to label that transmitted wave. And the other will be the reflected wave. So I'm just going to label both. Reflected wave. And you can just make a note to yourself. The reflected wave gets inverted when it reaches a fixed boundary. Or at the fixed end. Okay. So this produces a standing wave. And a standing wave has two components. They have nodes and they have antinodes. Well, the whole reason that a standing wave occurs is because you have wave interference happening. You have a generated wave and you have a reflected wave, and they're interfering with each other. So standing waves are produced by wave interference between the generated wave and the reflected wave. So there are points on that standing wave that I'm going to, actually I'll just go right onto this diagram. There are points on that standing wave that will actually appear to be not moving at all. And these points that appear to be not moving at all are referred to as nodes. So all those dots I just drew, including this, are nodes. And those nodes are points where destructive interference has occurred and the amplitude is 0. So there's no displacement happening at those points. They appear to be unmoving. On the other hand, you get these maximums that look like little bubbles because, again, you have your generated wave and you have your reflected wave. And we refer to these bubbles as antinodes. And antinodes are points where constructive interference has occurred. so in the diagram that I just drew for you, let's first look up here. Let's count how many nodes we have. So points of node displacement, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 nodes on this top chart. And how many antinodes? Well, it's the bubbles in between, so it's always going to be one less. So we have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 antinodes. Okay, let's go on. Oh, I'm running out of battery. Let's go on this other diagram over here. Let's see how many nodes we have. 1, 2, 3, 4, 5, 6, 7 nodes. And let's see how many antinodes we have. 1, 2, 3, 4, 5, 6. 6 antinodes. Okay, just so that you can identify the parts of a standing wave. Well, here's a problem that you might solve for standing waves, and you already know everything you need to know about standing waves except for one small detail. If we were to count how many waves here, we only look at the generated wave. We're not concerned with the reflected wave. So how many wavelengths do we have here? Well, we have 1 lambda, right? There's a full wave. 1. We have 2 lambda. And then we have 3. So here we have 3 lambda, 3 full cycles. Okay, so now I gave you this problem and I'm going to walk you through solving it. Hopefully my phone doesn't die. A drill attached to a rope at position A. That's why I labeled A over here. Let's just say the drill is attached over here. Position A. Generates a wave, and the drill is rotating at 40 hertz. So it's generating this standing wave we see above. I want to know the wavelength if the distance from here to where the drill is attached on this rope is 3 meters, but we have 3 lambda here. So each wavelength is going to be what? So I said find the wavelength and the speed of the wave. Well, we have 3 waves here, but it's 3 meters long. So we know that 1 lambda is going to be 3 meters divided by 3 cycles, because we just want to know how long is 1 cycle to find wavelength. So we have lambda is equal to 1 meter. Now I want to know the speed of the wave, so I'm going to use v equals f lambda. Okay, speed of the wave, I gave you the frequency is 40 hertz, so v equals 40 hertz times 1 wavelength, which is a meter. In other words, the speed of this wave is 40 meters per second.